Hi everyone, welcome to the next session of design and drawing of reinforced concrete structures. In last class, we have discussed about the what is meant by flanged beams and what is meant by L beam and what is meant by T beam. For isolated L beam, isolated T beam, as well as for continuous L beam and continuous T beam, how we have to calculate the effective width of the flange. These are the different type of procedures we have discussed in our previous lecture. Today we are going to discussing about the analysis of flanged beams. In analysis of flanged beams, based on the depth of the neutral axis, we are having three conditions. The first condition is case 1, that is we are taking the first condition as case 1. In case 1, what we are considering means we are taking the depth of the neutral axis lies within the flange. Again, one more time, I will explain about this flanged beam. If you see here, this is the one type of T beam. In this T beam, we are having the width of the flange as BF, as well as depth of the flange we are having DF. This is the depth of the flange. The depth of the flange having a depth of DF. And if you see, observe here, this is the web portion for this particular beam, and this is the area of the steel reinforcement we are providing in the beam. And in top side, in already previous class we have told about this portion is called as a flange portion or slab portion. In this flange portion, slab portion also we are providing the reinforcement. That reinforcement details we are not discussing here. That will come in sixth chapter, that is either in slabs it will come. And if you see here, this is the web portion. In web portion we are providing the steel bars. Based on the moment acting on the beam, we will provide a number of bars based on our requirement of cross sectional diameter of the bar. And again, if you see here, from this top of the outermost compression fiber to the centroidal distance of the reinforcing bars, we are taking this we are taking the effective depth of the beam as D. From top of the compression fiber to the centroidal distance of the reinforcing bars, we are taking this depth as effective depth, already we have discussed. And the gross depth we are taking as from the top of the compression fiber to the outer surface of the concrete beam, we are taking it as the depth of the beam. And from this bottom of the outer surface of the flange to the bottom of the web, we are taking this as depth of the web. This portion is called as the depth of the web, and this portion is called the width of the web. For analysis of T beams based on the depth of the neutral axis, we are having the three conditions. The first condition is when the neutral axis is lying within the flange. That means if you observe, this is the flange. When neutral axis available within the flange, then how the compressive forces are acting on the beam, how the tangential forces are acting on the beam. For such type of beams, how we have to design the beam, that we are discussing in our first case. And the second case, if you observe, in second case what we are considering means we are considering the neutral axis is within the web portion. That means if you see in first question, this is our neutral axis. Neutral axis, it is the axis which divides the compressive force and tensile force. From this neutral axis above, we are having the compressive forces, and below this neutral axis we are having the tensile forces. For this particular beam, how much amount of compressive force are acting on the beam, how many numbers of tensile force are acting on the beam, we are calculating. If you observe for this particular T beam, this is similar to the beam what you are designed for the singly reinforced beam, doubly reinforced beam. The same procedure we are adapting here for this particular type of T beam. When neutral axis is lies within the flange or lies in the flange, in this for this such type of problems, we are adapting the same design procedure as well as same analysis procedure for the singly reinforced beam. What you are discussing, the same procedure we are discussing. If you see here, this is the depth of the neutral axis, and for this we have to write the various type of assumptions from the limit state of collapse under flexible condition. That means plane section remains plane and parallel to the even and after before bending. The maximum strain in the concrete will be taken as 0.003 under flexible condition, as well as the stress block parameter is parabolic from neutral axis to the strain of 0.002 and rectangular to the strain of 0.0035, as well as the tensile strength of the concrete we are taking in the tension zone, it shall not be less than 0.002 plus 0.87 Fy by Es. These are the different types of assumptions we have discussed in our first lecture, that is assumptions of limit state of method of collapse under flexible condition. The same assumptions for T-beam also we are considering. If you see here, this is the diagram for stress diagram for the concrete, and if you observe here from neutral axis to the strain of 0.002, the stress block is parabolic. From this neutral axis to up to the strain, this stress block is parabolic. Again from 0.002 0.0035, the stress block is rectangular, and the compressive force acting on the stress block at outermost compression fiber at a strain of 0.0035, we are having the compressive force of 0.446 FCK. If you observe in our first lecture, that is assumptions of limit state method of collapse under flexible condition, we have discussed all these parameters, how we are calculating the compressive force for the rectangular section, as well as how we are calculating the compressive force for the parabolic section. All these parameters we are already discussed for the design and analysis of singly reinforced beam section. Hence we are not considering again the same design for this particular type of the T-beam. And if you see here, by calculating all this equating the analysis of compressive force for this rectangular portion as well as for this parabolic portion, we are having the total compressive force having a depth of the total compressive force acting on this particular rectangular and parabolic C equal to 0.36 into FCK into B into XU. This FCK into B into XU nothing but width of the flange and this depth of the planes. Whereas in our particular condition we are considering taking the, instead of total width of the beam, we are taking this as BF, that means width of the flange. In the previous rectangular condition, for rectangular type of beam, we are considered the width of the beam as B. If you observe here, for this particular type of the beam, we are considered the width of the flange, that is BF. That means total compressive force C equal to 0.36 into FCK into BF into XU. This is the force acting on the rectangular portion as well as acting on the parabolic portion. The same total compressive force already we have calculated. And again, if you observe in this bottom side, we are calculating the tangential force acting on the beam. The tangential force T equal to 0.87 into Fy into AST. This is also one type of force acting on the concrete member. Due to both in the equal and opposite compressive force and tangential force, it develops a couple. That couple will be acting at a distance of D minus 0.42 of XU. That means lever arm. The lever arm distance we are taking from this total compressive force to the total tangential force. That lever arm we are taking this value as D minus 0.42 into XU. This lever arm also how we are calculating for different types of beams. Already we have discussed in our previous class. In your examination, they won't ask all these analysis procedure. They will ask only the design procedure. This is the complete how the compressive force and tensile force acting on the beam. After calculation of all these total compressive force and total tensile force, we have to calculate the moment of resistance. That moment of resistance of the concrete of the beam is nothing but, suppose if you want to calculate the moment of resistance for compression zone, that moment of resistance for compression zone MORC equal to compressive force into lever arm distance. Compressive force into lever arm distance. As well as if you want to calculate the moment of resistance for the tension phase, for moment of resistance for tension phase equal to total tensile force into lever arm distance, where 0.36 into FCK into BF into XU is the total compressive force acting on this particular T-beam when the depth of the neutral axis lies within the flange. Again, if this depth of the flange it exceeding the depth of the flange, that means depth of the flange is greater than less than the depth of the neutral axis. What is the depth of the flange here? If you observe here, for this particular condition, df is greater than xu. That means depth of the flange is greater than depth of the neutral axis. For such type of condition, we have to analysis and design the beam by using this procedure. Next, we are having the two more condition, that is nothing but depth of the flange is greater than 3/7 of xu, or uniformly stressed, non-uniformly stressed, two types of conditions are there. After completion of this, that condition also we will discuss. And if you see here, and where this total compressive force C equal to 0.36 into FCK into BF into XU, as well as total tangential force equal to T equal to 0.87 into Fy into AST. From the distance between the resultant of compressive force and tangential force, we will get the lever arm. That lever arm is nothing but D minus 0.42 XU. We know the total compressive force, we know the total tangential force. Based on that, we will calculate the moment of resistance for the compression as well as moment of resistance for the tension. This is the design and analysis procedure for the flanged beam when the depth of the neutral axis is greater than the depth of the neutral axis. Next, we are having the two more condition. For this particular type of problem for analysis of flanged beams, when depth of the neutral axis is within the flange, you need not to do anything what you are designed for the singly reinforced beam. Instead of just B, we should have to substitute the width of the flange as BF. In previous condition, we have kept the value as width of the beam B for the rectangular beam. If you observe here, this is our T beam. For this T beam, what we have to do means just we have to keep this BF instead of the width of the flange, instead of the width of the beam. That is the condition. This is the procedure and analysis of the singly reinforced beam. How the analysis or expected problems we have to solve for such type of problems, you will see here. This is step by step procedure. Already different type of expected steps for the singly reinforced beam, doubly reinforced beam we have told, we have discussed about this. The same thing also we have repeating for this T beam also. How we have to calculate this moment of resistance for the T beam? That is nothing but first we have to calculate the step 1. First we have to calculate the limiting depth of the neutral axis. The limiting depth of the neutral axis based on the grade of the steel. What type of grade of steel you are using, based on the grade of the steel, the limiting depth of the neutral axis it will may change. First, for such type of problems, for calculation of moment of resistance for T beam also, they will give the all the parameters. They will give the depth of the flange, they will give the width of the flange, as well as they will give the total depth, width of the web and depth of the web. All these parameters they will ask to calculate the moment of resistance or moment capacity of the section in the compression, as well as moment capacity of the section in the tension. Such type of problems we have to use these following steps, and we have to design and analyze the beam. And if you observe, the first step is when they will give the in problem as width of the beam, as well as depth of the flange, as well as FCK grade of concrete, and Fy grade of the steel, and total depth, as well as width of the web. All these parameters they will give in the problem. For such type of problem, you have to follow this design step. The step 1 is calculate XU limit. That step already we know. XU limit equal to KD, where K is the neutral axis constant, D is the effective depth of the beam. 0.53D, 0.48D, 0.46D. These are the different types of limiting depth values based on the different types of grades of steel. This is 0.53D we are having for Fe 250 grade, 0.48D we are having for Fe 415 grade, and 0.46 we are having the value for Fe 500 grade. Based on this grade of steel, we will use this limiting depth of the neutral axis. Next, we are having the actual depth of the neutral axis. How we are calculating this actual depth of the neutral axis is nothing but total compressive force acting on the beam equal to total tensile force acting on the beam. That total compressive force equal to 0.36 into FCK into BF into XU. How we are calculating this means already we have discussed in our first lecture of assumptions of limit state of collapse under flexible condition. Here this is the force. Force is nothing but stress into area, where BF into XU is the this particular total depth for the rectangular beam. Whereas if you consider for our particular condition, the depth of the beam we are taking, that means the area of the beam we are taking this neutral axis depth as well as this width of the flange. The only thing is for singly reinforced beam design what you are discussed, that same discussion also we are doing here, but instead of B we are taking the width of the flange, that is BF, that is 0.36 into FCK into BF into XU equal to 0.87 into Fy into AST. Okay, from this we have to calculate the actual depth of the neutral axis, that is total compressive force equal to total tensile force. The tensile force equal to 0.87 into Fy into AST. From this we have to calculate the actual depth of the neutral axis as XU. XU equal to 0.87 into Fy into AST divided by 0.36 into FCK into BF, where 0.87 is the value we are getting from the factor of safety of the steel, and Fy is the yield strength of the steel, that is Fe415, Fe250, Fe500 based on the grade of the steel, where AST is the area of the steel required for the beam to resist. Here for the such type of problems they will give this area of the steel bars also. Okay, next we are having 0.36. FCK is the characteristic strength of the concrete and BF is the width of the plane. Suppose if you observe here, this is our particular T-beam. For this particular T-beam they will give this width of the plane as 400 mm, 500 mm, 600 mm based on the requirement of the loading condition. Okay, this is the calculation for the step for the depth of the neutral axis. Next step we are having the comparison of the actual depth of the neutral axis as well as limiting depth of the neutral axis. This actual depth of the neutral axis we are calculating by using total compressive force equal to total tensile force, whereas limiting depth we are calculating based on the grade of steel we are using for the particular concrete member. From this we are having the formula when if XU is equal to the XU limit, that means actual depth of the neutral axis will be equal to the limiting depth of the neutral axis. In those conditions we are naming it as balanced section. If actual depth of the neutral axis is equal to the maximum depth of the neutral axis, then we are taking this value as a balanced section. For designing of balanced section we should have to take this XU max value. For designing the balanced section, for analyzing of balanced section we should have to take this value as XU limit or XU max. Again, if you XU is less than equal to XU limit, that means actual depth of the neutral axis less than the limiting depth of the neutral axis. In such condition we are naming it as under reinforced section. For under reinforced section we are taking the value as XU. For under reinforced section we are taking the value as XU. And again, if you XU is greater than XU limit, for over reinforced section also we'll take this XU limit, but over reinforced section we won't design, we'll design it as a balanced section. Again I will repeat this, all this what is meant by balanced, under reinforced and over reinforced. In balanced section concrete and steel will both fail at simultaneously, hence why we'll use the concrete most of the sectional member to design as a balanced section. Whereas if you consider the under reinforced section, in under reinforced section we are providing the steel less compared to the balanced section. Whereas if you consider the over reinforced section, in over reinforced section we are providing the more steel compared to the balanced section. Due to provision of more amount of steel in the section, the concrete area it will may get reduced and concrete will fail first, it won't give any alarm, hence why we won't use any section as a over reinforced design section. This is the comparison of XU and XU limit. And next we are having the moment of resistance of the concrete as well as moment of resistance of the tension zone. That means in compression zone how much the moment can carry the beam, as well as in tension zone how much the beam can carry the tension, that we have to calculate. That is nothing but moment of resistance equal to total compressive force into lever arm, as well as for the compression, as well as moment of resistance for tension equal to total tensile force into lever arm. That step we will discuss here. I am writing here the moment of resistance for the total compression as well as moment of resistance for the total tensile force. That is nothing but compressive force into lever arm as well as compressive force into perpendicular distance. Next we are having the step number 4. Step number 4 we are having that moment of resistance for the compression. Moment of resistance for the compression. Moment of resistance for compression we are having compressive force into lever arm distance. That is compressive force we are having 0.36 into FCK into BF, where BF is the width of the flange. That is 0.36 into FCK into BF into XU. BF into XU. Next we are having the lever arm distance. That lever arm distance is nothing but D minus 0.42 into XU. D minus 0.42 into XU. This is the calculation procedure for the moment of resistance for the compression zone. Next, as well as we are having the moment of resistance for the tension. Moment of resistance we are having the for tension phase as again total tensile force into lever arm distance. Tensile force again we are having 0.87 into Fy into AST. This is the tensile force acting on the beam. The tensile force equal to 0.87 into Fy into AST. Again lever arm we are having the distance of resultant of total compressive force minus total tensile force. That is nothing but D minus 0.42 into XU. This is the complete analysis of flanged beam when the depth of the neutral axis will be greater than the depth of the flange. This is the depth of the flange. This depth of the flange is greater than the depth of the neutral axis. Next we are having the one more condition, that is nothing but suppose if the depth of the neutral axis lies within the flange. If the neutral axis is here, how the total compressive force acting on the beam, how the total tensile force acting on the beam, when the depth of the neutral axis is in this web portion, how the moment of capacity of the section for the compression as well as moment capacity of the section for the tension, we'll see in a subsequent lectures.